Let's get the chat going. Cool. All right. So today we're talking about comparing distributions. We'll go into what that actually means and why we would do that. But that's kind of the main goal for today. And then we'll kind of conclude with hypothesis testing, which is something we've basically already been doing. And then on Wednesday, we'll go into how do we actually make decisions with incomplete information. So what that basically means is we've seen some examples where we wanted to assess whether a model is accurate or not. And typically, so far, it's been really clear cut. But there'll be some situations where the values that you simulate look kind of like the value observed, but not quite like it. And so this is kind of like edge cases there. So we'll go over that on Wednesday. And then Friday, we'll go into A/B testing, which is like comparing two different populations. So in terms of announcements, we have our midterm on October 16th, 7 to 9 p.m. Pacific time. Again, it's going to be up to and including A/B testing. We'll have some review material on Piazza for you there. And we also have our new vitamin as usual, due before Wednesday's lecture. And homework 6 is due this Thursday. Turn it on Wednesday for a bonus point. And then lastly, homework 7 is a little bit longer, so we're going to release it a little bit earlier on Wednesday, but it'll be due the following Thursday as usual. And then lastly, please check out this guide on random functions. So we started going over some different ways that you can randomly sample data. And so we have a few different ways to do that. This goes through the different ways that we've learned so far and clears them up, shows you exactly how to use them. So please take a look at that. That's going to be important for the midterm for sure. All right, so a bit of review for what we covered last time on Friday. We introduced this concept of models. And so basically we said a model is essentially just a set of assumptions about the data. And so in data science, most of these models will involve assumptions about processes that involve randomness or chance. And so that's why we call them chance models. And the key question we're going to be typically asking is, does the model fit the data? And so we had some examples of this last time where, we had the jury case where there was only 8 out of 100 people in the jury were Black. And the model that was being claimed by the, local region was that they were sampling people randomly from the population of that city in order to determine who gets onto the jury. And so we knew that 26% of the people in that population are Black. So that was basically their model. Their model was 26% of the people are Black in this population, and we randomly sampled them, and we got 8 out of 100 randomly. So that was the model, and we assessed whether the model actually fit the data. And so how did we do that? Well, firstly, if we can simulate data according to assumptions of the model, we can learn what the model predicts. So in that case, we could simulate what happens if 26% of the population is Black and you actually randomly sample people from that population. So we actually did that. We simulated that many times. Sometimes we got like 15 people out of 100 that were Black. Sometimes we got up to like 35, but we never really got any jury simulations where there were only 8 people out of 100 that were Black. And so that's essentially what we did was we simulated kind of the predictions of this model or kind of just outputs of this model many, many times. And then we compared it to what we actually observed. So what we actually observed was 8 out of 100, and we compared it to all the simulated juries that we created. And so we simulated a jury of 100 people. We did that maybe 1,000 times. And then finally, to make a conclusion, you just check whether the data and the model's predictions are consistent. So in that case, they were not consistent because we never saw 8 out of 100 in any of the simulated values. And the lowest one we actually saw there in that case was like 15 out of 100 were Black. And so that's evidence against the model. So that's evidence, in that case, it's evidence against the model that people were randomly chosen from the population. And then if the data is consistent with the model, then that is evidence for the model. And so that was the case in the second example where Mendel's pea plants, he claimed that 75% of plants are going to be purple. And so we actually simulated a bunch of flowers according to that assumption. And we saw how often they were actually purple. We compared that to how often they were actually purple in his example of 929 flowers. And we saw that things were more or less consistent there. So what he actually observed was like 76% of them were purple, And 76 seemed to come up quite a bit. There were even many times there were like 78% purple or things like that. So that was kind of how we compared it there. And so typically there's going to be two viewpoints when you're doing assessment of models. And so we'll go over some examples of what these viewpoints exactly were in the two examples we've seen so far. And we'll call these the model and the alternative. So in the jury selection case, the model was that the people in the jury panels were selected randomly from the eligible population. And the alternative viewpoint is that no, they were actually biased against black men. So those were the two viewpoints we were assessing there. And then the genetics example, again, we had the model, which is that each plant has a 75% chance of having purple flowers. And the alternative viewpoint was that no, it doesn't. And so you can see here the viewpoints are slightly different. In the second example, we were just saying the chance of getting purple is just not 75%. Like maybe it's 78%, or maybe it's 72%. So basically it could be much higher than 75, it could be much lower than 75. So that's the alternative viewpoint. In the jury selection case, the alternative viewpoint is that they were biased against black men. So it's a very specific kind of alternative viewpoint. So we weren't just saying that, it wasn't randomly selected. We actually were being really specific in saying it was actually randomly selected, or it was actually selected against black men. And so the alternative that you frame will also decide how you actually test the model. Like what statistic do you actually choose to compare between the simulations and the observed values. And so we'll go over how those were chosen as well. So just to recap, like actually formally, how do we assess the model? So the first step is we choose a statistic to measure the discrepancy between the model and the data. And so the statistic is going to then be simulated under the model's assumptions. So recall, a statistic is just a number that you create from a sample of data. So you've observed some data, you can create this statistic out of it, and then you can also create the statistic out of any data that you simulate from a model as well. And so that's the basic idea. So you have your observed data, it has its observed statistic, then you simulate a bunch of data under the model's assumption, create statistics for each of those simulations, and then just compare the distribution of the simulated statistics with the actual statistic that you observed. And that's essentially what we did. So we said we would draw a histogram of the simulated values of the statistic, which came from our simulations, and then we just computed the observed statistic from our actual single sample that we observed. And then we just saw how far our observed statistic was from the histogram. So in the case of the jury, the statistic that we chose was just the percent of people that are black out of 100. And so the observed statistic was 8 out of 100, and the simulated statistic was all the different values that we saw there. So sometimes it was as low as 15, sometimes as high as 35%. And then in Mendel's, the pea plant case, the statistic was a little bit different, because what you want is typically like really large values or really small values of your statistic to be evidence against the model. And so in the jury sample case, we got 8 out of 100. And so we wanted basically like larger values of the simulated statistic would be evidence against the model being true, because basically that's inconsistent with the data where it's really low. In the case of the pea plants, the alternative was just that, no, it's not 75%. So in that case, you want large values to be evidence against the model and low values to be evidence against the model. And so when you have a situation like that, where like both large values and small values are evidence against the model, then it's really common to make your test statistic just the absolute difference between what you observe and what the model is claiming. So in that case, what we did was we said, let's take what percent of the flowers are actually purple, subtract that from 75%, and then take the absolute value of that. And so that will give us then a value that is going to be large when there's evidence against the model. Because let's say we observed 100% of them were purple, that would be evidence against the model, because 100% minus 75 is 25%, that's large. And then similarly, if you had like 50% observed were purple, 50 minus 25, the absolute value of that is also 25. So basically 50 and 100 would both be equal evidence against 75%. But of course, the concept of what is large, that actually depends on the histogram itself. So the histogram of your simulated statistics is going to determine whether 25% actually is large. Because if you did simulate, let's say from the model at 75% are purple, let's say you simulated like 1,000 times, and you see a lot of histograms where like 100% were purple, and then many times the percentage that were purple was like maybe 45%. In that case, 50 and 100 maybe isn't actually that far. Maybe that's actually pretty reasonable and something that you would expect to happen, even just by chance. But the histogram basically gives you a sense of how crazy is the observed value that you saw. Is your observed value really unreasonable if this model is true? Or is it something that we would expect to see if we simulated from it? That's essentially what you're assessing there. And so that's why we kind of compare to the histograms. So with that framework kind of set up, let's try to do some examples of coming up with a test statistic for each of these kind of questions. So the basic premise is that you have some data and it's results of 400 tosses of a coin. And we're going to have two different kind of models that we're going to try to assess. So in the first case, we're going to assess the model that this coin is fair. So like 50% chance of getting heads. And the alternative is going to be that no, it's not fair. And then secondly, we'll do another experiment where the model is the coin is fair. And then the alternative is going to be no, it's actually biased towards heads. So heads comes up more often than tails. So the probability of getting heads is like more than 50% essentially. So with both of those things in mind, just try to think of what statistic you would choose for each of these kind of scenarios. Okay, so let's try to go over the answers here. So remember, the statistic that you're going to choose, it actually depends on the alternative hypothesis. So if you notice here, sorry, not alternative hypothesis, but alternative viewpoint. So if you see here, the model is the coin is fair, that's the same for both of these scenarios. But in scenario A, the alternative viewpoint is no, it's not fair, whereas the alternative viewpoint in B is a little bit more specific. It's saying not only is it not fair, it's actually biased towards heads in particular. It's a very specific viewpoint. So we can go over the answers here. So for both of these, if you guess that the answer is just like the proportion of 400 that comes up as heads or the number that comes up as heads, that's a good starting point. That seems like a valid statistic for both of these. And if that is your statistic, that means that a number of heads around 200 is going to suggest fair. So that seems like the correct thing. But you have to be just a little bit careful here. So in the first case, very large values of the number of heads is going to suggest not fair, but also very small values of the number of heads is going to suggest not fair. Because remember, the alternative viewpoint is that it's just not fair. So if you get like 25 out of 100, or 25 out of 400, let's say, that's like a really small number of heads. So that's probably going to be like evidence against the model. And similarly, if you got like 350 out of 400, that's a lot of heads as well. So basically really large values and really small values of the statistic, in this case, would be evidence against the model. So in that case, you wouldn't want to do just the number of heads itself. You want to use the distance between the number of heads and 200, because that way, whether the number of heads is large or small, the distance from 200 is going to be large. That's the key. And so this case, the statistic for scenario A should actually be the number of heads minus 200, and then take the absolute value of that. So this is very similar to the p-plant example, where it's claimed that 75% are purple. Alternative viewpoint is, no, it's not. Therefore, use the distance from 75%, absolute value of the distance. And so once you have your statistic in this absolute value form, this enables your statistic to be such that large values of it are going to suggest evidence towards the alternative, essentially. And so that's typically what we want. We want like really large values of the statistic to be evidence for the alternative, or really small values, that's fine too. But you don't want both. So in this case, if you had a really small value of the statistic, that means that the number of heads is close to 200. So that's actually evidence for the model. So that's actually a good thing. So this is correct here now. So you just want to make sure like either only really large values are evidence against the model or only small values. If you have a situation where both large values and small values are evidence against the model, that's not ideal. And so, yeah, and so in this case, we subtract 200 because we just want to see how close the number of heads is to 200. That's essentially what this is saying. So if you get something like 300 out of 400 are heads, that would be your test statistic would be 100 in that case. And then if you got like 100 out of 400, the test statistic would also be 100. So like an equal distance above 200 is going to be the same kind of amount of evidence as the equal distance below 200. And then in the case of situation B, large values of the number of heads would suggest bias towards heads. So in that case, that means you could just use the number of heads. So that's kind of the difference here. So in the second scenario, just the number of heads alone, that's fine. Because basically, if I have like 400 out of 400 heads, that's a lot of evidence that it's biased, the coin is biased towards heads. Whereas if I get like 25 out of 400 heads, that's evidence against that alternative viewpoint. It doesn't seem like it's biased towards heads if I'm only getting 25 out of 400. So small values are not evidence for the alternative in that case. So that's the main thing you want to think about is as this number gets larger in magnitude, it's more evidence for the alternative. And if you can satisfy that condition, then that is a good statistic for that alternative viewpoint. Why don't we do, someone asked, why don't we do number of heads minus 200? You could actually do that as well. That'd be valid too. So number of heads minus 200 would be fine. In that similar situation, really large values would be evidence for heads being biased towards. Small values would not be evidence of that. So that's actually fine. You could do number of heads minus 200. What counts as large? Typically, we're just going to be talking about just like bigger positive values. So the more positive it is, the larger it is. So if you look at the case of situation A, you're taking the absolute value of the number of heads minus 200. So that's essentially just saying that like the larger that number is, like the more positive it is, that's more evidence for the alternative. Whereas the closer that number gets to 0 or negative, that's more evidence for the model. In this case, it's absolute value, so this statistic will never be negative. But basically, closer to 0 would suggest fair, larger values would suggest not fair. And that's going to be the case for both of these, actually. So even in situation B, smaller values in terms of the number of heads is going to suggest more evidence for the model, whereas larger values are going to suggest that, okay, actually, it's actually biased towards number of heads. So for part B, it seems a little funny that smaller values would suggest fair. But basically, it's not really saying that it's fair, but it's just saying that it's more evidence that it's fair than it's evidence that it's biased towards heads. So that's really the key distinction there. It's really kind of saying, there's the distinction between the two viewpoints. So smaller values is going to be more evidence for the fair viewpoint than it is towards the heads bias viewpoint. In part A, wouldn't small values be for the model? Yeah, that's correct, exactly. So in part A, small values are for the model. That's exactly what you want, actually. So in both of these situations, you want to find a statistic where small values is for the model. All right. So I think let's move on. So those are some examples of how we chose statistics in a couple different scenarios. Now let's go to comparing distributions. And so in this case, we're going to do another jury selection example. This is actually in Alameda County. And in this case, it's going to be slightly different because we're going to have like more than 2 races involved. So in the initial jury example, basically the population was like 26% black, and then the rest of the people were white in that population. In this case, we're going to have several different races involved. And so it's a slightly different way of assessing the model here, but it's a similar setup. So you have eligible jurors in a county, and then that's how you create your jury. So jury is usually created from them. And the actual process where it works is you have your eligible jurors, then you have your list of like eligible residents who can actually serve on the jury. Then you kind of get them onto a jury panel, and then you actually determine the jury itself. So that's kind of the typical process. And so part of our kind of civil code actually says in California that all people selected for the jury need to be selected at random from a source that's kind of representative of the population of the area served by the court. So if you're creating a jury in Alameda County, the people that are selected for jury should be kind of selected randomly from the population of people who live in Alameda County. And so let's take a look at what this data actually looks like here. So in our case, I've already written this down here, but basically we're going to create a table that's going to have 3 columns here. So the first column is going to be ethnicity. So this is going to be the actual ethnicity of people in Alameda County for the purposes of this jury selection. So we have Asian, Black, Latino, white, other. And then we have eligible, which is the proportion of people belonging to each ethnicity amongst the population that's eligible to be on a jury in Alameda County. So like in Alameda County, 15% of eligible people for the jury are Asian, 18% are Black, 12% are Latino, so on. And then finally, we have panels, which is the actual proportion that we observed of people who ended up being in each of these categories. So in actuality, 26% of the jury was Asian, only 8% was Black, 8% was Latino, so on. So you can see how what actually came up is slightly different than the eligible population. So let's take a look at all of these together. So we can now see them side by side. So again, here, 15% of the Asian population is, or 50% of the population that's eligible is Asian, but 26% of the population that was actually on the panels was Asian. 18% of the population that's eligible is Black, but 8% of the panels were actually Black, and so on. So again, the eligible basically comes from the entire population of people who are eligible for the jury. The panels column comes from what we actually observed happening in maybe several, in an example panel, let's say. And so there's a clearly discrepancy here, right? And the big question that we want to ask is, was this panel really randomly selected? The people in this panel, were they really randomly selected according to this breakdown of ethnicity in the eligible population? And so it's possible that they were randomly selected. Just by chance, you might have happened to get like a lot more Asian people. You might have just happened to not get as many Black people. It's certainly possible by chance, but we want to get a sense of, how likely really is it? Like, is this something that we would really expect to see, or is it going to be like really crazy, really, really rare? And that's the basic idea. So let's also visualize this. And so just looking at the numbers, because I think that makes it a little bit easier too. So we'll do jury.bar H ethnicity. And so here we can see the bars. And so this is basically showing us the distribution of ethnicity for each of these 2 groups. So you have the eligible population, that's the blue bars. And then you have the panel, the observed panels, which is the gold bars. And so you can see right away that, the proportion of people in the panels that were Asian seems to be much higher than the proportion in the eligible population, whereas for Black and Latino, it seems to be the opposite. So you can see kind of the breakdown, and this is essentially distribution, actually. This is a categorical distribution of people in the panels versus people that were eligible. So we can see that difference. And then the idea is the model is claiming that the people in the panel were selected randomly from the jury. So let's actually write this out. So the model is going to basically be all of the information that's in this ethnicity column. So let's just grab this. And so this is essentially what our model is. And then if we wanted to simulate a new jury panel from this model, we could do that using sample proportions. So we could say simulated equals sample proportions. And then we pass in how many people we want. So in this case, this was a panel of 1,423 jurors, and we'll simulate from the model. So the model is, again, the eligible population distribution. So we'll simulate it one time and then take a look at the results here. So here we've simulated one time, and so here we get that what sample proportions is going to do is it's going to sample 1,423 people, assuming that this is the breakdown of ethnicity of each individual person that can be chosen randomly. And then it's going to automatically calculate what percentage of the sampled people are in each of those categories. So we basically created a sample of 1,423 people, and it turns out that 0.148 of them are Asian, 0.18 are Black, and so on. So this is just kind of doing a lot of the work for us, essentially. So 1,423 people were randomly sampled. That was what happened. And then we calculated the percentage of people that are in each category. So it does all the work for us. And so we can see here that this is like pretty similar to the proportions of the eligible population, right? They're not differing too much. I mean, Latino was supposed to be 12%, we got 11%, that's pretty close. White was supposed to be 54%, we got 53.9%, so pretty close, all these. And then what we can do is we can add this back into our table and take a look at all of them side by side. So we'll do jury with simulated equals jury with column. Let's call this simulated. And we'll just pass in our single simulated jury panel. And then let's look at all this together now. So now we've added a new column here called simulated. And so you can see we have our eligible distribution of ethnicity. We have the actual distribution on the panels, 1,423 people. And then we've simulated another 1,423 people from the model and looked at what results we have there. And so we're not doing the full-blown simulation right now where we do like 1,000 simulations. We're just doing one example. So I just want to show you what happens when you simulate one time. So we'll get to that. And so now let's actually visualize this in a histogram as well, or sorry, in a bar chart, because this is categorical. So here we have a bar chart now, and so now we've added this new kind of sky blue color, which has the simulated breakdown. And so again, this is just one simulation. And so for this one simulation, it looks like the eligible and the simulation proportions are pretty similar across the board here. And whereas the gold ones look quite different for a few of these ethnicities. So that's kind of interesting. But again, that was just one simulation. Maybe it was just chance that it looked really similar to eligible. What we'd really want to do is do this many, many times and then compare, you know, how that looks compared to the actual panels. And that's the actual proper way to do that. But in order to actually do that, we need some test statistic to be able to compare, you know, our panels to our simulated jury panels. And so in previous examples, it was pretty simple. Like when we did the jury panel where we were just looking at the percentage of people that were Black, the test statistic was just the proportion of people in the jury that are Black. And that was our test statistic. And so we just kind of compared that single one that we observed, which was 8 out of 100, and then we simulated several jury panels of the size 100, like 1,000 times, and looked at what percentage of those were Black. So that was a single number that we could compare between the two. But in this case, it's kind of hard. Like there's not one number. We need to come up with one number that summarizes what the jury panel looks like. And then similarly, we need to be able to calculate that single one number per simulation and then compare that single number, because that's what a statistic is. We need to come up with one number. And so in this case, it's a little bit harder because you can't just compare like one particular ethnicity, because you may not get a good answer. Like if you just compared white, for example, here, you might not get the right result. If you compared just Asian, that also maybe wouldn't be correct. So you want to come up with a single number, even though we have like all this information here. And so we'll go over what that number actually is. And so this is actually a new statistic that we haven't used so far. And the basic idea here is this number is actually going to give us the distance between two distributions. And that's going to be what we're going to use here. So the context for this is, you know, we have people on the panel from multiple ethnicities, and the distribution of the ethnicities is categorical. And so if we want to see whether the distribution of ethnicities in the panel is actually, close to the eligible jurors, we have to measure the distance between the two distributions. So between the eligible distribution and the panel distribution. That's what we need to do, essentially. And so one way we can do that is we can try to summarize the distance between the two distributions using a single number. So let's actually try this. So we have all of our information in jury. So one thing we could do is we could maybe just take, to start, let's actually just take the difference between these distributions. So let's take the gold bars and subtract the dark blue bars from them. So let's actually do that here. So we'll call this diffs for differences. And we'll do jury.column panels, and then we'll subtract jury.column eligible. So we're just going to take the difference between each of the ethnicities between each of these two distributions. And then we can actually add this into the table as well. So we can just visualize it all together. So we'll do jury with column difference. And the difference is just going to contain the diffs that we calculated. And then we can finally go look at what this is. So here we have, again, eligible, the panels, and then the difference. So basically what this is saying is that, the Asian population, there was the difference between the percentage that was Asian in the panel versus eligible was positive 11%. For Black, it was negative 10%. For Latino, it was negative 4%. For white, it was like basically 0, and so on. So we're basically calculating a difference here. So this is one way that we could try to think about the difference between the two. And then if we wanted to summarize now, we have the difference between these two. If we want to combine this all into one number, what are some ways we could try to do that? We have these differences here laid out for us. Take the average, someone said. You could add them up. Yeah, let's actually try that. So let's take jury.difference, we take column difference, and then let's do np.sum, let's say. So let's sum them up. Okay, so here we get something kind of strange. So we get like 2.77 e to the minus 17. So what's happening here is this is essentially 0. So what this is saying is that the sum of all these numbers is 0. The reason it's not exactly 0 is because there's some rounding error here. Remember we talked about how floats don't have like infinite precision. They can only represent up to a certain number of digits. But this is basically 0. And the reason for that is because the sum of this entire column, all the panels, is 1, because the sum of all the different categories has to be 100%. And then the sum of this is also 1. So if you take their difference and sum them up, you're basically just taking 1 minus 1. And that's why the sum of all this needs to be 0. So it's always going to be 0, actually, the sum between the difference of any two distributions. So that's the right idea. You guys are really close, but there's some extra step there. And someone said absolute value. So you're kind of onto something there. So absolute value is essentially what we're going to actually do here. So this new statistic, we're going to call this the total variation distance. And that's going to be how we summarize all those differences into a single number. So the way it's going to work is, again, for each category, compute the difference in proportions between the two distributions. That's what we just did with the diffs. Then we take the absolute value of each difference. Then we sum them up. And then we'll also divide the sum by 2. And we'll explain why we divide by 2 in a second. But it's very similar to what we just did. So, we computed the differences between the two distributions, but then before we sum them up, we'll take the absolute value, and then we'll divide by 2. And so let's go back to the demo and do that. So again, here we already did the first step, which was we took the difference between these two columns. So that's what we got here. And then what we needed to do was actually take the absolute value before we take the sum. So we can actually write this out here. So we actually want to take the absolute value of the differences, then we take the sum, and then we divide by 2. And so then we get an answer of 0.14. And so this is essentially how we're going to do it. And so this 0.14 is like kind of weird. Don't really know exactly how to interpret it. But it basically gives you a sense of like how far apart these two distributions are. And the idea is the larger this number is, the more far apart these two distributions are. And the reason we divide by 2, intuitively, one way to think about it is you have these negative differences here, and then you have these positive differences here, right? So you have some of these differences are negative, some of them are positive. So we're really just trying to take an average of like the negative part and the positive part. That's kind of one intuitive way to think about it. But the basic idea is that now we actually have a way to calculate a statistic. If we observe a jury panel, we can calculate this statistic. It's basically just how different is the jury panel from the eligible jury panel. And so now we have a way to calculate it. And what we're going to want to do now is we're going to want to simulate a bunch of jury panels from the eligible population and then calculate their differences, each of their differences to the actual eligible jury panel. So if we're going to do that, we're going to want to make a function for it. So let's actually write this out as a function. So we're just going to call this TVD, and then it's going to expect 2 distributions. So distribution 1, distribution 2. And then what is it going to do? Well, we can just write this out. So the first step is take the difference between the distributions. So dist1 minus dist2. Once you have the difference, then we take the absolute value of the differences. Then we actually sum it up. So we can sum up the differences, and then finally we divide by 2. So kind of 4 steps there. Take the difference, then the absolute value, then sum it up, then divide by 2. And now we have a function to take the difference between any 2 distributions. And so we can save our actual observed TVD. Let's call it observed TVD. And we can call the function to get the value again. So again, this value we already know up here is 0.14, but we're just going to write it again here using the function. So the TVD is going to be the distance between the jury.column eligible, or sorry, panels. Actually, doesn't matter which one you put first, and eligible. So let's just make sure our function's working as expected. And so here we get 0.14. And then we could also do the same thing, but see what happens when you take a simulated value. So we could do TVD between sample proportions 1423 and the model, which is the eligible population, and then compare that to the eligible. And so here we just did one simulated. We simulated 1423 people from the eligible population to be selected for a jury, randomly selected, and we compared the TVD of that distribution to the eligible. Oops, sorry. And in that case, we got a total variation distance of 0.01, so much smaller than the 0.14. So now you can get a sense of what does this 0.14 mean? Is it large? Is it small? This gives you kind of a hint here. So again, we've done this now, and this is an example of doing it with one simulation. And of course, to actually show some strong evidence, we'd want to not just simulate one time, we'd want to simulate, 1,000 times. And so let's actually do that. So firstly, let's actually write a function, which is just going to simulate the TVD itself. So it's going to do it all in one shot. So we'll call this simulated TVD, and then it's just going to return essentially what I ran here one time. It's just going to return that. And so now we have a really simple way to simulate one total variation distance of one simulated jury panel. And then we can finally do our simulation. So we'll make an array, which is going to store all the results. And then we can specify the number of simulations we're going to run. So let's do 1,000. And then we will actually do our simulation. So once again, we'll do for I in np.arange num simulations. And then what are we going to do in each simulation? Firstly, we're going to simulate a new total variation distance. So simulated TVD, and then we will append this to our array so that we can store it, store the value. And so if you run this, what this is going to do is 1,000 times, it's going to simulate a new jury panel of 1,423 people, then calculate the total variation distance of that simulated jury panel with the eligible population, and then store that total variation distance in this array. So that's essentially what we're doing here. So any questions before I continue here? Can we explain why we divide the sum by 2? So this is just kind of how the total variation distance is defined. We divide by 2 intuitively because you have, when you take the difference of two distributions, you have some of these values that are positive. So this was positive 0.11, this was positive 0.03, and you have some values that were negative, so negative 0.1, negative 0.04. So we just want to get a sense of kind of the average sum for the positive part and the negative part. That's the basic idea. The 1423, that's just the number of people that are in the jury panel that we wanted to assess. So this panels column here is referring to 1,423 people who were actually selected for the jury, and this was their makeup of the ethnicity there. And so we want to simulate this panel again. And so that's why every time we simulate, we're going to randomly draw 1,423 people. And so TVD essentially represents just kind of the difference between two distributions. So it's like, how far apart are they? Are they really similar to each other, or are they really far apart? That's all it's saying here. So in this case, what this is saying is these two distributions are like 0.14 far apart. Whereas when we did a random sample of 1423 people from the model, they were only 0.01 units apart. So. Okay, and so going to the simulation, how this actually works. In this simulation, what we want to do is, first step is this part here. So first step is simulate 1,423 people from your model. So the model is actually the same thing as jury.com eligible. So I can just write it like this, actually. The model is the same thing as this. So we can actually just replace all these cases with the model. So our eligible population is the model. That's the way we define the model. The model is the people who are eligible to be on the jury. And then, so the first step when you're simulating some new jury is simulate 1,423 people under the assumptions of the model, which is like the distribution of the ethnicity in the eligible population. Once you've simulated a random jury panel, let's get the distribution of people in that jury panel and compare that to the actual model, which is what's actually expected to be the proportion in the population, and then calculate the difference between those two distributions. And then we just do that process 1,000 times. So again, this is why we're calling the function again down here. So we'll call that 1,000 times. And then the idea is we want to see the variability of this guy. Like every time we randomly draw a new jury panel, right, we're going to get slightly different results. Like sometimes the jury panel is going to have a lot more Asian people than expected. Sometimes it might have more Black people than expected. It's going to jump around a little bit. And the idea is we want to get a sense of how much does it really jump around, and how is that like jumpiness of the sample, how does that compare to what we actually observed here? And so that's why over here, we've also calculated the total variation distance of what we actually saw. So panels is what we actually observed with the model. And we got a total variation distance of 0.14. We basically want to see whether the total variation distance of our simulations, how does this move around compared to what we actually saw? Because it's very possible that the 0.14 is actually something that could happen by chance. Like we might just simulate some values that happen to be as different as 0.14 or maybe even more. So that's the basic idea there. We just want to compare, how much do our simulations differ from the model compared to the observed panel difference. So once we've run our simulation, the last step is to plot everything on a histogram, plot the simulated TVDs. So I'm just going to write this out here. So the title of this graph is going to be simulated TVDs if the model is true. And then we'll make some bins here. So 0 to 0.05, 0.005. Don't worry too much about the bins that I'm making here. And then we're going to, in order to make a histogram, we have to first make a table. So I'm just going to make a single table with a single column. Column name is going to be title, and it's going to contain the TVDs that we simulated. And finally, draw a histogram with bins equal to the bins we just specified. And then just to add the context, we'll also print out the observed TVD. So that's the observed difference of our jury panel from the model. All right, so observed TVD was 0.14, remember. That's how different our actual jury panel was from the eligible population. And then down here, we're going to plot a histogram of simulating a jury panel from the eligible population, just chosen at random. And so if we chose them at random, this is the distribution we get. So sometimes the TVD is like really low, sometimes it is large, but it never really gets much larger than like 0.045 or so. So no matter how many times we like randomly created a jury panel, just randomly picking 1,423 people, we never got a panel that was as different from the eligible population as like 0.045 or so. Whereas what we actually observed, the difference was 0.14. So what that's telling us is that the observed jury panel is really, really different from the eligible population compared to what you would actually get if you just randomly chose people from the eligible population. So essentially, this is evidence against the model that people were actually chosen randomly. They were not. They likely were not chosen randomly. There was probably some bias there. So that's essentially what this is telling. And so that's how we can interpret this. So again, the 0.14 is telling you how different the actual jury panel was from the actual jury panel of 1,423 people was from the population. Whereas these simulated values show us all the different types of differences we could get if we just randomly pick people. So like one time we got a simulation where the difference was actually like almost zero. So the population that got chosen was actually like pretty much spot on with the eligible population. And then sometimes it was very different because by chance you just might pick, a few more people of a particular ethnicity. So in that case, we had a difference, of like 0.04. But we never saw a difference as big as what we saw with the actual panel. That's the main key here. So that's total variation distance. And so again here, just summarizing what we did, we wanted to assess whether a sample was actually drawn randomly from some known categorical distribution, which is the eligible population. We chose TVD as a statistic because we wanted to measure the distance between what we observed and what the actual distribution should be or what's claimed to be. And then what we said was, okay, so we know how different our actual sample is from the population, but now we want to understand how big is that? Like 0.14, what does that mean? Is 0.14 really like crazy number, or is that something we're going to see? Is it something we should expect? So in order to assess that, we sampled at random from the population many, many times, computed the TVD of each of those simulated juries from the eligible population, and then compared a histogram of them. And so we essentially looked at the empirical distribution of the simulated TVDs, compare that to the actual TVD. And in our case, the actual TVD was much higher. So that was evidence against the model. And so this whole process of what we've been doing, it's actually called hypothesis testing. So some people alluded to this earlier. So you've taken statistics before, you might have seen this, but we've actually been doing hypothesis testing so far. And so just to kind of go over what hypothesis testing really entails is, you're just choosing between two views of how the data were generated. So this is just analogous to the model and alternative thing we were talking about before. And so these viewpoints are actually just called hypotheses. And the idea is your test is going to pick the hypothesis that's better supported by the observed data. So this is just kind of a different language for talking about what we've already been doing. So this isn't actually anything new compared to what we've been doing so far. But it's just some formal language around it. And so that model and alternative, typically in this framework, we call them the null and the alternative. So a lot of times you'll see this like in papers or in articles on the web. But basically, the method only works if you can simulate data under one of the hypotheses. So you need to have some well-defined chance model that you can simulate from. And so in our case, we always had a good model that we could simulate from. Like, 26% of the population is Black. That's something that we can simulate from. 75% of the flowers are purple. That's something we can simulate from. And then same in the case of the Alameda jury panel. We had, a bunch of different races, and we knew what the percentage of people in the population are for those races. Therefore, we can simulate what a jury might look like from that population. So that part's really important. And so typically the model that you can simulate well from is going to be the null hypothesis. And then that's why many times you'll see this phrasing under the null hypothesis. So you're basically simulating data under the assumption that the model is true. So that's what we just did in this case. We assumed that the jury panel is taken at random from the model, from the eligible population, and we simulated under that assumption. So we simulated under the null hypothesis. And the alternative viewpoint was like, no, it's actually biased. It's not actually randomly sampled from this eligible population. And then the statistic that we choose to simulate and that helps us decide between the two, that's called a test statistic. So again, we've already been using this. This is just formally what it's called. And so the main thing you want to think about before choosing a statistic is, what values of this statistic is going to make us lean towards the null, what values are going to make us lean towards the alternative. And preferably, you want to choose a test statistic such that higher values lead towards the alternative. And you want to avoid any statistic that says both high and low values are going to give us evidence for the alternative. Again, if you have a situation where the statistic you're proposing, if you realize that, oh, both high and low values are actually going to be evidence for the alternative, then you're probably going to do something like take the difference from something and then take the absolute value. So that's test statistics. And then finally, we have prediction under the null hypothesis. So the actual idea then is you want to simulate this test statistic that you've chosen under the null hypothesis many, many times. So we did it 1,000 times today. And then we would draw a histogram of the simulated values. And then that histogram of those simulated values is called the empirical distribution of the statistic under the null hypothesis. So it's basically a prediction of what the statistic might look like if the null hypothesis is true. And so it shows like all the likely values of the statistic and how likely they are as well. So in our case, we saw some TVDs like close to 0, but not that many. And then there are a lot more TVDs around like 0.1 or 0.01, and then just a few TVDs around 0.04. And so the thing to keep in mind here is that these probabilities are approximate. We can't actually generate all possible random samples. So, we just did 1,000 samples today, but there's maybe like 1,000,000 different ways that you could create a jury panel of 1,423 people. And ideally, you'd want to be able to get all 1,000,000 possible ways that you could draw those jury panels and then look at the distribution of the TVDs. But that's not really a practical thing to do typically. And so that's why we'll just typically simulate like 1,000 or a couple thousand and then compare that. And that's typically going to be good enough because as we saw with the law of large numbers, if you have like pretty large enough sample size, it's going to look pretty similar to what the actual distribution is of your statistic. And lastly, sorry, I know we're over time, but this is the last slide. So basically the idea is we need to decide between the null and the alternative. And the way we do that is we compare the observed test statistic with the empirical distribution simulated from the null hypothesis. And if the observed value that we saw is not consistent with the distribution of the simulated values, that means that the test favors the alternative. Typically, you write this as data is more consistent with the alternative. And so deciding on whether a value is consistent or not with the distribution, the visualization may be sufficient. So far for us, the visualization has been enough. Like we can just look at the histogram and our value was like really far off of the histogram, or it was like right in the middle. So far we've been able to do that, but there might be situations where it's not that clear cut. And so in that case, there's some standards that we have, which we'll go over in the next lecture. And so to go over what that means, if I go back here, this value of 0.14, if you look at this histogram, it only goes up to 0.04. So we know that the 0.14 is like way, way far out of the histogram. So it's really obvious just from visualization that the data is more consistent with the alternative. But let's say instead that the observed TVD was like 0.04. So it's like right here, it's like on the edge of the histogram, but there is some simulated values beyond it as well. So in those kinds of situations where you're kind of like near the edge, then just looking at the visualization isn't enough. You have to actually compute something there. And so we'll go over that in the next lecture, how we actually do that.